Okay, here is our first video problem for conservation of energy. So we have a ball, it falls on a spring, the spring gets compressed. So we're interested in how much this spring gets compressed as a result of this ball dropping on it. So the way we're going to approach this is, well, first let's draw an axis. So we'll have this vertical axis be our y-axis, and we'll put a horizontal axis going through here. So this is the final height of the ball. Now, let's label our axes. There we go. So the initial, so we're going to solve this problem using conservation of energy. We're going to look at the total mechanical energy when the ball is being held up in the air. So that's position 1 that I just labeled, and position 2 when the ball fully compresses this spring. So let's look at the initial energy. So our total mechanical energy is the sum of our kinetic and potential energies. Well, this ball's held at rest at position 1 before it's dropped, so it doesn't have kinetic energy, so that term is just 0. And the potential energy is just the energy due to the height of the ball, and that is m times g times the height. Now the height is 1 meter plus delta y. We're taking our origin at 0, so when this ball finally comes to a rest, it's at a height 0, so its initial height is going to be this 1 meter plus delta y. There. So that's our initial energy, and now, so that's our energy at position 1. Let's look at our energy at position 2. This is just, well, again, it's the sum of our kinetic energy at 2 plus our, I changed colors there momentarily, plus our potential energy at 2. Now, this ball, it falls, it gains kinetic energy, but as it interacts with the spring, all that kinetic energy gets converted into potential energy of the spring. So our kinetic energy at position 2 is 0. And our potential energy at 2 is just the potential as the energy stored in that compressed spring, which is given by the formula 1/2 times the spring constant K times the amount our spring is compressed squared. So the law of conservation of energy says that our energy at position 1 should equal our energy at position 2. So we plug in what we've already got. We have mg times 1 meter plus delta y is equal to 1/2 k delta y squared. Okay, so actually what we have here is a quadratic in terms of y. So let's write it out. It's 1/2 k delta y squared minus mg delta y minus mg, and that should equal 0. So we can use the, well, let's plug in when we plug in our numbers, we end up with the following coefficients in our quadratic. We should get 3.75 delta y squared minus 0.0245 delta y minus 0.0245, and that should sum to 0. Well, we're looking for solutions for when the left-hand side is equal to 0. There's many ways we can go about solving this. Perhaps the easiest is using the quadratic equation. I'm just going to write down what the answers are. Solutions to this are delta y equaling 0.0842 meters and negative 0.0776. Now, delta y is going to be positive. It's a positive distance. So we don't have to consider this negative value, and so the amount our spring is compressed is just 8.4 centimeters.